So if you take a look at this picture, this is sort of a stylized version of what we do in particle physics. We run our experiment, combine it with theory, produce results which we eventually want to publish. And this talk will focus on this arrow in particular and how workflow management systems can help us. So first, I will give a little bit of motivation for workflow management systems for data analysis. Then I take a look at existing workflows which we have in HEP and discuss two approaches and our experience with them. So first of all, if we look at the landscape of physics data analysis, I will do this in two dimensions. First the scale and then the complexity, which I define in a minute. But let's start here. Here you are running everything on one computer. You have the data, you have the software, you're your own boss, and everything is nice. But in reality, we have large data sets, many files, many events. So this is the scale here. And we cope with that with parallelization and running on the grid. And this is working really nice and will work nice in the future as well. And we also heard some improvements regarding this already here at the conference. So the complexity is a bit more fuzzy because this contains all the advanced features we want. We want, for example, multivariate analysis, where we might need to split our data sets, where we might need special hardware, for example, GPUs. We might want to work in collaboration with our colleagues and want to use advanced algorithms. And if we do this with small data sets, we can cope with this if we have good scripts, if we share our code with repositories, we can handle it. But if we have large scale and high complexity, this becomes more difficult. And I think this is the sweet spot where workflow management systems can help us. So if I can start from scratch and make my wish list, I have two groups, basically. The first is regarding the analysis and also the conformability. So this has to fit in how the collaborations work. So first of all, we want reproducible, final, and also intermediate results. The whole system has to be adaptable. For example, in a review process, people might ask you to change something in the analysis. This should be easy to do. And also there might be new recipes, for example, in a collaboration. Then this should be possible to work with other people, either at your institute or a different institute. And for the development, but also for the processing. For example, if you have a group and you have all the members of the group have shares in for computing resources, you can share them together. And there shouldn't be any limit regarding frameworks or even programming languages. This should be completely free to choose. So the second group here is about the operations, how you do the analysis, and it's mostly about convenience. So ideally, this should be like when you compile code, you write make, and all the dependencies are created or are built. And this should be done in a distributed fashion to cope with a large scale. It should be opportunistic, so we should be able to use different run and storage locations. And this is, I think, very important, the automation. I don't want to do the bookkeeping. I don't want to remember where I stored which files and the conditions on how they were created. I don't want to make sure that the data is actually available at the worker node. This should be done automatically. So, and the last point is justice choice. It has to be done in some language, and Python is widely available and also used, so this is choice. So if we take a look at a picture of just an example analysis, it starts with a selection and ends with some measurement. And now let's get a little bit into the language of workflow management system. So if we think of this whole analysis as a workflow, then we can see it's made up of smaller workloads. So here, for example, select and reconstruct. And we also see these are connected And whether we are aware of it or not, this is a clear interface, because the reconstruction can only work if it knows what the selection has done. So there is already an interface. So for this to do all these steps in the analysis, we need computing resources. We need CPUs, which we could do locally or on the grid. And we also might need something special for our deep networks, for example. We might need a GPU. And also we need storage. And all these steps might have different needs regarding the software which has to be available. And if we look at analysis in these terms, we see there's an overlap to workflow management systems. So if you start looking about workflow management systems in HEP, this is what you will find. Mostly Monte Carlo production. And it's always the same steps. Event generation, path on shower, simulation, digitalization of the front-end electronics, and finally event reconstruction. So this is a very linear chain. And sometimes parts are changed. Maybe a new version of a generator is available or a different generator, but the chain remains more or less static. And this is a very important process in HEP. And that's and also because it produces large amounts of data. So this leads to special infrastructures which are built for the Monte Carlo production. This means special databases, high storage availability, and also workload management systems. But this static chain is not flexible enough if you want to run user data analysis. So we need something different. And now I'm going to discuss two approaches, which I call the report-based approach and the target-based approach. So the report-based approach is tailored from scratch for HEP and for our infrastructures. And the idea is that every time you run a command on any of your payloads, a report file is created, and this contains metadata, for example, which files have been produced and where are they stored. And the idea is this should perform well if the storage is slow or if it's hard to access the storage. Because the report has to be read only once, but can be the information can be accessed multiple times in the future. So the target-based approach, there we thought, can we use community software and build on top of that, so we don't need to do it from scratch. And the idea is to look like the make program would do directly if the dependent file is available. So there's always a lookup on the storage. And so this means we don't need the reports and we reduce the complexity. But the question is, will it work also with, for example, the Dcache, when it might be sometimes slow to access? So this is how the report-based approach works. The user is here in the bottom and created some Python file which contains the definition of all the analysis steps in the analysis. And now the user wants to run one of those steps. So it communicates via a command line interface with the scheduler, which takes one of these steps. And the steps know about the predecessors and knows the dependencies. So the scheduler can look what are the actual tasks which have to be performed. For example, if you do the event selection and you have maybe 10,000 files which you have to run, then for each file to run on each file would be one task for each file. So then the scheduler can combine multiple tasks and send them as jobs to a run location. On the run location, you have to make sure that the right software is available. So first, it will look at the binary storage location if a precompiled software package is already available. If not, it can download the source code, compile it, and then store the compiled version on the binary storage location. So for the next job, it's already available. Then it will download the input data, only the parts which is needed, runs the payload, and stores the output data back up to the data storage location. And since this is the report-based approach, it will also generate one report, which is stored in the metadata storage location. And so the scheduler can check these reports and knows about the status of the job or of the step execution. So this has some nice benefits. For example, if you combine, let's say, 10 tasks into one job, and it wasn't possible to retrieve the input data of one of these files, then the report will contain this information, couldn't get the input data, so the scheduler already knows I have to resubmit it, or it can inform the user to check what's going on. So we don't have to wait for the whole job with all the 10 tasks to finish until we find out, oh, something went wrong. So I showed you a picture of the stylized analysis before, and this is a picture of a real analysis. All these little ellipses are steps in the analysis, and the lines are the connections between them. So each line indicates that some kind of information from this step is needed in some of the following steps. And because it's so tiny, I just zoom in so you get an idea. For example, here I have some boosted decision tree training steps, and then the weights which are produced here are used, for example, for systematics evaluation in an electron and a muon channel. So now let's take a look at the target-based approach. The idea is similar, but now we use the Luigi pipelining toolkit, which was first developed by Spotify and now is a community-driven open source tool. And we adapted it so that it can work with the HEP infrastructure. And the main difference is that here, if you want to run something, every time there's a check whether the necessary input file is already available. And in practice, this looks something like this. You want to run this task, and which is the trigger task, and this will build a dependency tree, and it will figure out I need the input from this task, which needs this one, and so on, and then it will start running in the bottom, and you kind of can see like bubbling up these green circles until finally the triggered task is also performed. So now about our experience. One more thing, the software. Yeah, right. We want to be as opportunistic as possible. That means we want to use the software that is available at the run locations if we can. So we do something like the dynamic bash RC to pick and choose the software which is available. But sometimes that's not enough, and we have to be proactive. And this is what I mentioned before. We build our own software and store it precompiled. And then what we do is eventually we create like a sandbox for each task when it's executed. So we can execute multiple tasks at the same run location, and they can have different software environments. In the future, we might also explore containers and lightweight virtual machines. At the moment, we couldn't test this because the grid sites we use don't support this, but this could also be an option to make the deployment more easy. Okay, so what did we reach so far? We tested both approaches with cross-section measurement with the CMS data, and basically what we did is we didn't build a framework to write analysis, but we built a toolbox to do the meta steering of the analysis. It's basically a design pattern how to write analysis. All the input parameters are transparently encoded, so we have a reproducibility with our analysis. We can go back, even if something has been done 2 years ago and we don't really remember how it was done, we can look at it because everything is in the steering. So this creates a make-like environment where you can run distributed your analysis, and where you focus on the physics and not on executing the analysis. And so this is the main paradigm shift which we propose with workflow management system. You focus on defining the analysis and not on executing it. So I have 2 more points which are consequences. For example, if we look at how collaboration works, and I try to sort this loosely, like upper part we have more work, and in the lower part we have more collaboration. So if you want to apply something someone else has done, you can look at the written documentation on the web page or on papers or the slides, and it's very tedious because sometimes details are missing and you have to basically implement everything yourself from scratch. And what you can do is you can share data. For example, you can have histograms with weights, or someone produced tuples which you use then for your own analysis. You can share code fragments with either old school via email or with shared repositories. But if you really want to work on the same analysis, you can share a workflow. You have the same code and the same files, and if it has already been run by someone else, you can just reuse it, and you actually work on the same analysis. Okay, just want to mention these two efforts, the data preservation and high energy physics. They obviously want, one of the goals is to have tools for adding value to data, and I think workflow management does that. And HEP data also wants to save and store the results, and not only the final results, but also how the analysis is done. So for you to take away from this talk is, I think the trend for larger scale and larger complexity will continue, and I think workflow management systems are really helping, and this can be a gateway also to data to analysis preservation in the future. Thank you.
Thank you. Any questions? Do you have a repository for these workflows?
There's a repository for the report-based system, but in the future we're focusing more on the target-based system. And this is, at the moment, we are trying to separate it from the analysis, which is like the beta tester analysis. So it's not yet in a separate repository, but will be.
So if you want to test out the container-based stuff, so you might know that at CERN IT we're looking into like analysis preservation and workflow systems. So we're using YADIT and the common workflow language. We're starting to look into that, and something like the report-based stuff would be nice there as well. And this takes away maybe this constraint that you need to run on grid size, because we run our own infrastructure. So if you want, you can try to test it out.
I know that CERN offers this opportunity, but we also had to focus on our data analysis and had to get things running, and that's why we didn't put time into that. Thank you.
Yeah, I think the idea of using a make mental model to specify the analysis is very interesting. There is, in fact, there's a group at the University of Notre Dame that develops a tool called MakeFlow, a workflow system which resembles very closely GNU Makefiles. It might be something you want to compare the system.
Interesting. I haven't heard about this.
I imagine this language is not as bad as GNU syntax.
No, what you do is, maybe I have. You do something like this. You write a Python class, and it's based on Python. So you can write a small class, and basically in the run method you specify what you want to do, but you can also call external processes from here.